Hello everyone, this is Roger from Wave Computation Technologies. In this tutorial, I'm going to show you how to use the software Wavenology to design a dipole antenna. So before I start it, I need to first make sure that you're clear of some textbook theories about dipole antenna calculations. So basically, for a dipole antenna to radiate, its first resonant mode is called half-wave mode. That means the current distribution along your dipole antenna looks like this shape. It's like a standing wave, okay? So if your dipole length in total is 20 centimeters, for example, then actually the single wavelength in that frequency will be actually doubled. That means wavelength is 40 centimeters, okay? So if the dipole is radiating in free space, then you can calculate the first resonant frequency of your design by the formula over here, which is the wavelength equal to the speed of light divided by your frequency. Then you put your frequency over here, and that means your speed of light divided by lambda. So as we said, if the wavelength is 40 centimeters, then that would be 3 e to the 8. This is speed of light in free space approximately, divided by 40 centimeters, and that will be 0.4 meters. So that will be 750 megahertz of your first resonant frequency of your dipole. This is in the textbook, okay? And then the radiation pattern will be something like, it's very popular, called donut shape. Okay, it looks like this. So for the second resonant mode, that will have 3 standing waves. It can be drawn like this way. Okay, you have 3 of them, and that means you will have 1.5 wavelength within the 20 centimeters. Okay, so if you calculate that, you will have 3 e to the 8 meters per second divided by 20 centimeters divided by 1.5. It gives you 13.33, and then times 100 centimeters. So this is simple calculation. That will be 2.25 gigahertz. Okay, at that frequency, second resonant mode. Keep in mind of these numbers we calculated. So if we can go on and on, the next mode will be 5 of the standing waves here. Okay, 5. So if your total length is 20 centimeters, you will need to divide by 2.5 in order to obtain the wavelength of that frequency, resonant frequency. So if you calculate that, will be 3 e to the 8 meters per second divided by actually 8 centimeters, because 20 divided by 2.5 is 8 centimeters. So after that, you will find this is a frequency 3.75 gigahertz. Okay, that's your third mode, as we calculate it even by hand, by imagination here. Okay, according to the textbook theory. So you have a kind of a clear picture of how to do the calculations in math. But now let's do the design in the 3D simulation software. So this is a new project, and then I click the design tab, and this is a design dialog. First of all, you need to make sure your unit is convenient for you. In this case, I'll select centimeters. The rest I leave it as default. I click OK. Background, I choose it to be air. And then the boundary, I know in the XY direction, so I just choose as open -2 centimeters, and I specify this 2. XY is very symmetric, so I just repeat that, and I click here to be 2 centimeters, and I click. The frequency, let's just choose 0.1 gigahertz to 6 gigahertz. Okay, click OK. Then the mesh is typically, I'll just use more denser mesh to get better result, more a good sampling of the results. And then everything else I'll leave it as default. Okay. So if I click OK, this will be the box. You can take a look. Alright. This is the main box. Next, I need to create my dipole. In this case, I'll just use a rod, a metal rod, set as PEC. So I click over here, cylinder. Then I choose my material to be PEC. Of course, it has advanced options. You can plot a center hollow cylinder, but in this case, if you specify this to be 0, then it's just a cylinder. And the radius, I put it as 0.1 centimeter. That means 1 millimeter only. And I want my origin to be started at 0.2 centimeters in z direction. And I make my length of this rod to be 9.8 centimeters. So add together, you will see this is 10 centimeters. I'll leave a little gap in the middle. Okay. So click OK, you will see this rod is plotted correctly. You can rotate and check its shape. Those are good. And then you can do another one. You can either mirror it, or you just, in this case, create another one. Simple enough. Again, the inner radius is 0. And then the radius keep the same as the previous one. And origin, I want it to be started at minus 0.2. And height, I want it to grow negatively along z direction. So I'll just put a negative 9.8 centimeters. So click OK, you will see it's plotted. Zoom out a view, you'll see this rod. Okay, so that's as simple as that. It's just very simple geometry. Material is just set it to PEC or any other metal you like. Okay, so next you need to put a source. Right here, you do a lumped source and create lumped source, asking you to pick up 2 points. You just basically pick up any 2 points, and you need to make sure the position is correctly entered. That means I started from the origin, so xy is 0, and then I want it to be minus 0.21. So I make it a little bit penetrate into the negative z rod. Then I want it to be along this direction, positive 0.21 rod. Okay. Just click OK. You will see there's a lump port created. If you zoom in, you can find that. Whoops. Let's go back again. You will see this lump port is touching the metal, and it's correctly connected. Okay. So now I have a correct excitation. This is voltage lump port. All right. So basically, that's all you need. You can just save the project and start a simulation, and it will be very fast. It only takes about 1 to 2 minutes to finish the entire simulation. And then I've finished the simulation already, so we can take a look here. The result. This is identical to the previous design. And then I can calculate my S parameters. That means in this case, you only have 1 port. So that means S11, which is the reflection coefficient. So you double click over here, the magnitude, you can check it. So there is several resonant, the sink of the S11 indicating the energy is radiating out. So let's check the frequency here. So the first one, the S11 goes down about 15 dB. You can see the frequency is right around 0.685, approximately 0.7 gigahertz or 69 gigahertz. Okay, so that's the first resonant frequency, which is not 750 megahertz. I'll explain why in the later demonstration. So let's keep in mind of this first resonant frequency. And then the second one, as you can see, it's 2.125 something gigahertz. So that's the second resonant frequency, okay, over here. And then as you keep going, the next resonant mode, you can check. The frequency is around 0.58 gigahertz, okay. So this is the dipole antenna, and according to the 3D simulation, it shows the resonant frequencies this way. But if you recall what I have said, what we've calculated before, the theory that according to the theory of the simple dipole calculation resonance, the first frequency should be 750 megahertz, and the second one should be 2.25 gigahertz, and the third one should be 3.75 gigahertz. So it's a little bit off, okay? And let's see why that happens. And that actually explains why you need a 3D simulation to capture this effect. Okay, so in reality, the theory is based on an infinite thin dipole antenna, which means your rod has a zero in the radius. It's actually a thin wire. Okay, but in reality, the dipole antenna is always modeled by a metal rod with a thickness. So if it has a thickness over here, let me show this. As you can see, if the cylinder has a thickness, like this way, then it creates a capacitance. Okay, so your entire system have a little capacitance over there. And what does this capacitance do? It actually stores some energies, and then actually make this wire in the eyes of electromagnetic waves to be longer. That's the what we in a simple terminology called stretching effect, because of this capacitance effect. Okay, so if that's the truth, then we can expect as the thickness of the wire is thicker and thicker, this wire looks like longer and longer in the eyes of EM waves. Until it's really infinitely thin, then it should be converged to the theoretical solution as we predicted before. So in order to demonstrate this phenomena, I did another simulation over here, which is doable in Wavenology to do a parametric analysis. That means everything else I keep the same. I only sweep the width of this wire, the thickness of the wire. So the value I can show you here is the parametric analysis. Is from actually 0.2 millimeters to 1 millimeters, and I need 5 value of them. So I sweep that. Okay. So this simulation is already finished. I just show you the result of the resonant frequency. Okay. So you will see that. Okay, let's zoom in here. This effect is very obvious. The blue one is the thinnest one, which means 0.2 millimeters. The purple one actually is the thickest one, which is 0.1 centimeters. I'm sorry. Okay, so you do see that the frequency is dropping off towarding 0.68 gigahertz. As it gets thinner and thinner, it goes towards the ideal value, which is right over here, 0.75 gigahertz. Okay, and for the second one, the phenomena is even more obvious. The frequency is all dropping down as it's getting thicker, and it's going to the better value, it gets thinner. The third mode is the same. Okay, remember the third mode is 7.5 here. It's definitely off, but it will converge to there if it goes to infinite thin. So that explains why the frequency is shifted a little bit lower than the ideal and theoretical predictions. Okay, so that's about a dipole antenna over here. We can also take a look at the input impedance of this thing. This is very general, how to say, well-known curves of the input impedance. The blue one is the real part, and the red one is the imaginary part in the frequency domain. Okay, so a very typical value over here, the first resonance, when imaginary part goes to 0, that's the first resonant frequency, which is around 0.68 gigahertz. Okay, let's see, it's right here. And the value here is about 72 ohms. Okay, that's a well-known value. So it's capturing that effect. All right. So this is about the dipole antenna. So you know all the resonant frequencies, and then let's take a look at the radiation pattern and the current distributions. Okay, so Basically, what I do is just set up another far field radiation and set up some snapshot definitions in the software, and run the simulation again, and then I can see the far field. So because I know the resonant frequency already, I can say, okay, first resonant frequency exactly at that point, 0.68. And then I display this, you will see this is the donut shape as predicted in the textbook theory. Okay, so this is how it looks like. You can also look at the logarithm view, just like a donut. Okay, now the second mode, which means you have 3 resonances, standing waves of the current. You will see this is the radiation pattern. Okay, that's how it looks like, the second mode. And the third mode, it will goes higher. Radiation is more directed, but with here you got some ripples, okay, of the other components in the radiation. All right. So you can also at any frequency set up a plane cut, and then display the 2D curves of your radiation pattern, as shown here, just at the first resonance. Okay. So that's how you set up the simulation like that, and then check the far field. Okay. You have also additional information about directivity, efficiency, radiation power, and gain, things like that. So one might have a question about, okay, why I cannot have a two standing waves along the dipole. The reason is quite simple. It's just because of cancellation. If you have one single wavelength distributed along the dipole of your current, then one is radiating going up, the other current is going down, and that generates the energy electromagnetic field is totally cancelled. Okay, because it is symmetric along the direction. So the energy is not going out, and it's totally reflected back to your source. That's why it cannot radiate. It has to have a odd number, not even number of your half wavelength. Okay. So the last thing, let's check about the frequency, the snapshot results. The first thing I want to show here is the transient signal. Okay, so I move it and I rotate it. I define a plane right near to the dipole, as you can see over here. Okay, and then I also define the surface current density along the dipole. So I zoom in a little bit, and then I like to see the log ones, and I add the field vectors. And you can see the current is flowing and it's radiating a field out. Of course, it's absorbed by the absorbing boundary conditions, and you can see it's just coming out. The field is coming out. And in transient, you can already recognize the resonance. Okay, but you cannot recognize, okay, where is the half resonance, where is the 1.5 and 2.5, where are they? But this is transient data. You will not recognize that. Okay, this is when the current is totally died out. This is transient data. You can also do a frequency domain snapshot. As you can see here, I just enter some frequencies. I enter that already, and you just display all of them. That will show you the here. And then in this case, I will turn on the current flowing along the wire, and you will be easily recognize the what I'm talking about the half wavelength. You can see the current distribution is right about strongest in the middle, and get almost to 0 at the end terminal. Okay, so this is about the half resonance of the current distribution. And the next mode will be, as I said, it is predicted exactly what happened. 1/2, 2/2, and 3/2 of your current distribution. Then that radiate at 2.125 gigahertz. And then the next mode, as you observed in the S11 parameters, This is 1, 2, 3, 4, 5. 5 standing waves of your half wavelength. Okay, so if you contain 2 of them as one single wavelength, that will have 1, 2 and a half, 2 and a half. Okay, this is how exactly the software can predict the physics and it can match the theory. And of course, if you can design all of this, you can now begin to design some advanced structures, bending this and have some other devices connected. That is where the full wave simulation software is getting more important. Okay, but to verify, this is convincing enough to demonstrate the accuracy.